Good day, folks. Welcome to my YouTube channel. Here's another electric circuit question. It's the June 2016. It's a national paper. Let's cut the chase. In the diagram below, three bulbs A, B, C are connected in parallel to a 12-volt source of a negligible internal resistance. So this battery, we're given the EMF there. It's 12 volts. It has no internal resistance. The bulb is rated 4 watts, 6 watts, and 10 watts respectively, and are all at their maximum brightness. We know that the brightness is directly proportional to power. The greater the brightness, the greater the power. So the one that is brighter is this one, and then followed by this one, and this one is less brighter than all of them. Right? It says now, if you look at this circuit, it's only parallel here. In parallel connection, we know the voltage is what is the same. So the only voltage that they use here is what is 12. Now in 9.1.1, it says calculate the resistance of the forward bulb. The resistance of the forward bulb, 9.1.1. So what do we have in the forward bulb? We have the voltage here. The voltage that is used here is 12, and it's 12 there, and it's 12 there. So we're going to use the formula that says V squared over R. We use that formula based on what we have. And then we have the power, it's 4 watts. And then we have the voltage, it's 12, and it's 12 square divided by R. If you do your method there, your voltage there, it's going to be your resistance, sorry, it's going to be 36 ohms there. Now in 9.1, how will the equivalent resistance of the circuit change if the 6 watt bulb burns out, which is this one? It burns out. These two resistors will continue working, but what's going to happen to the resistance here? Now, all the time, guys, when you remove a resistor in a parallel circuit, the total resistance increases. So the effective resistance there will increase. That's the answer there. Removing a resistor in parallel, it increases. So the answer there, it's increased. Now in 9.1.3, it says, how will the power dissipated by the 10-watt bulb change if the 6-watt bulb burns out? Right, increase or remain the same, or give reason for your answer. Now this question, it says how will the 10-watt bulb, it's asking this one, if the 6 ohm bulb burns out. So we said this one is going to burn out, but let's look at the 10 ohm resistor. Is there anything that is changing there? So if you look here in the 10-watt bulb, the voltage is still going to be 12, and its resistance is not going to change there. So according to this formula that says P is equal to V squared over R, the voltage is still the same and the resistance is still the same, so that means the power is going to be the same. So the answer here is what? Is no change. And then the reason for that, you will say there's still the same. The answer is no change because of same potential difference and resistance. The potential difference and the resistance are still the same, so that will give the same power there. I hope that makes sense, guys. With that, now let's go to the second part of the question. The second part of the question, it says a learner connects a high resistance voltmeter across the battery of 6 ohm. Now let's have a diagram for that. Here's the battery with an internal resistance, and then this battery, they connected a voltmeter there, and this voltmeter read what? 6 volts. So this 6 volts is the what? Is the EMF, right? Now it says now she then connects a 6 ohm resistor across the battery, and the voltmeter now reads 5 ohms. That 5 ohms is the what? Is the V external, right? So there's a resistor there. Resistor that reads what? 6 ohms. And then the reading now here is no longer reading 6 ohms. It reads what? 5 volts. Sorry, the 5 volts is the what? Is the V external. Sorry, there's a current that is moving there. So by connecting this resistor now, by connecting this resistor here, so the voltage that is used here externally is 5. And then the difference between that 6 and 5 is 1, which is there as the internal. So is the voltage that is used by that internal resistance. Now the question, it says calculate the internal resistance. So calculating the internal resistance there, how are we going to calculate that? What do we have, right? So what are we going to do in that? Okay, let me write it here, 9.2.1. So what do we have there? We can get the V internal. The V internal is the difference between the the EMF and the V external, right? So we will say 6 minus 5, which is 1 volts, right? Having that, we can say now the voltage that moves internally there, it's the 1 volts. But now we are looking for the current. We're looking for the current. So what are we going to do now that we have the V internal is 1? So what are we going to do? We are going to say V internal is equal to IR. We don't have the current that moves here. We don't have the current that moves here, or the current that moves internally, but we can get the current because we have a resistance here and we have the voltage that is used there, which is 5, the V external. So before I go there, so what I'm going to do, I'll say V, okay, let me use this. Let me say I is equal to V over R. I'm using the V external and using the R external. Sorry. The R external, the V external there is what? Is 5, and the R external is 6. So I'll say it's 5 over 6 ohms, right? From that, we go to the formula that says V internal is equal to IR. And then I know the V internal is what? Is 1. And this is not ohms, guys. This is amperes. So it's 5 over 6, the current, and the internal resistance there. So if I say I times and I divide by 5 over 6 both sides, 5 over 6. So I have an internal resistance. The internal resistance there, it's going to be 1,2. So it's 1,2 when I punch that in the calculator. There's so many ways to do that, guys. I hope that makes sense. Now let's look at the other part of the question. It says the learner now builds a circuit below using the same 6-volt battery. And when they use the same battery, guys, you must remember the internal resistance there, it's going to be the internal resistance that we just calculated. It's going to be 1,2 ohms, because if they use the same battery, this is the resistance of the battery, right? Now it says, and there is the 6 ohm resistor. So there's a 6 ohm resistor. Now she connects an unknown resistor R in parallel with the 6 ohm resistor. The voltmeter reads 4.5. Now look, here's the 6 ohm resistor. Now it's connected to an unknown resistor X, and then here's the battery, and then we are given the reading on the voltmeter there. So this reading on the voltmeter here is the what? It's a V external, right? It's a V external. Now we still have an internal resistance, which is 1.2 there, as I've mentioned. So what are we going to do now? The question, it says calculate the resistance X when the voltmeter is 4.5. So what are we going to do now? What are we going to do in order to get that? That resistor is parallel there, right? That resistor is parallel there. So now it's 9.2.3. 9.2.3. I skipped 9.2.2. I'm gonna go back to it. What are we going to do there? First, we're going to get the V internal. The V internal, how do we get the V internal first? We'll say V internal is equal to EMF minus the V external. Our EMF is still 6, but the V external, and which is this, is 4.5. So I'll say 6 minus 4.5, which is 1.5 volts. Now having that, the V internal there, it's going to help me to get the total current. So the next step that I'm going to do internally in that resistance internally here, the current that passes here is the total, but now I have an internal resistance, I have the voltage, the potential difference that is used there, which is the 1.5. So the next thing, I'm going to calculate the current. So I'm going to say V internal is equal to IR, and then I get the internal potential difference, and then the current that I want there, and then the internal resistance is 1.2, and I divide by 1.2 both sides. So if I divide by 1.2 both sides there, I will get the current that is 0.83 if I punch that in the calculator. I hope that makes sense. Having that current, the next thing that I'm going to do to get that, I'm gonna use the current that goes here. Remember, the current is 0.83, and then it splits and splits. So but the total current that is here externally is 0.83. So I'm going to use that current to get the R external. So I'll say R is equal to V over I, which is I'm getting the R external using the V external and using the total current. So the V external there is 4.5, and then we divide by the total current, which is it's 0.83. So doing so, when I punch that in the calculator, getting an answer of it's 4.5 divided by, no, I'm not correct here. So if I say 1.5 divided by 1.2, the answer is 0.125. I'm wrong here. The answer here is 1.25 amperes. So here I'm gonna divide by 1.25 amperes. So when I punch that in the calculator, when I say 1.25 amperes, the answer that I'm going to get there, it's going to be 3.6 ohms. That's the resistance, that's the external resistance. Remember, the external resistance, this is parallel, so the parallel here, the total is what is 3.6. So what I'm going to say, I'll say the R external is equal to R parallel, right? So now I'm going to use the parallel. I'll say 1 over parallel is equal to 1 over R plus 1 over X, right? I'm doing the resistance of these two in parallel using the parallel, which is now I got the parallel is 3.6. So the next thing I'll say 1.36 is equal to 1 over 6 plus the resistor that I want, which is X. So I'll say 1 over X is equal to 1.36, 1 over 36 minus 1 over 6. Remember, we want 6. So I'll do the inverse. So that remember we want x. So I want x, so I'll say x is equal to. So when I punch that, the entire thing in the calculator, I get what? 9 ohms. So the resistance there is 9 ohms, right? Which is the resistance X is 9 ohms. Now, this is the question that I've skipped. It's a definition of the EMF. Guys, it's a very important definition. When we talk about the EMF, we're talking about the maximum energy provided by the battery per coulomb passing, or per coulomb charge passing through it. There's a maximum energy provided by the battery per coulomb passing through it. Stick to the exam guideline when it comes to the definition, guys. Cheers, bye. Don't forget to subscribe. Don't forget to like all my videos and share with your friends and family. Cheers, bye.